The objective of this video is to understand chi-square distribution. I am familiar with the name but never quite actually understood what it meant. So in the course of today's recording session or study session, I will watch one of these particular videos, and once I'm done watching them, I will try to explain the key insights and key findings that helped in my understanding. Okay, this particular video from Very Normal is asking how which approach would I take, and the scenario is that there is a new drug from my company and it's been given to people, and now we have to compare the success versus failure of my drug versus placebo. So number one outcome is success versus failure, and immediately the first thing that comes to mind is this is a binary situation, so it means binomial. We want to compare the treatment against placebo, again the same thing, but we can recruit lots of people, so it means it could integrate different amounts of people, n types of people, right? So these kind of leads to me to believe that this could be a Bernoulli experiment as well. Let's see what is the answer. Okay, and the video is suggesting that we have basically a binary situation, and this is like binary but we cannot see it. It also, wait, what? Okay, and it's also suggesting that because we have two possible outcomes, this is a categorical data, and categorical data can have multiple categories. I have to check that one out, but the idea is that because we are comparing at the same time, this is like number two, the idea is that we can like yeah, I'm back, sorry. Because we have a comparison aspect, we are basically dealing with a two sample problem, and this is kind of a new thing for me as well. I'm not used to dealing with two sample problems, but let's see how that works out. So and the third one I want to mention is that both the independent and dependent variables are categorical variables. So this particular experiment or thought experiment, hypothetical experiment, whatever, deals with both independent and dependent variables, and both of them are categorical. So let's see how this problem progresses.
To analyze our migraine data.
Okay, we are going to, let's break this down into something. So we have the luxury of large samples, so why can't we use a proportion test? And apparently a proportion test is a t-test here. So a two sample t-test would be like this. I have no idea. This channel like describes, I think, two sample t-tests. Power explain chi-squared, no, cannot find it, but I'm sure like this channel does it, and this is like the title of the video, two sample t-test. But we are going to do something contingency wise, like contingency table, and we are going to contingency table method and then the chi-squared test. Apparently this is what we're going to do. So yeah, let's see what where this video particularly leads to. Okay, a bit more information on this. So the columns are influenced by the row category, that is one thing, and we have like this would be the subscripts here would denote like what column and what row. So like to take this example, this is the second column and the second row, second column, the first, oh wait, what, this is the first column and the second row, so the row number first and then the column number. Okay, row and column. Then we have, indicates column, yeah, row and column. These are called margins, so this particular margins probably would be set for a clinical trial, and this is a clinical trial, and basically means that the sample size would be like limited. Contingent is a way of saying that this thing, one thing depends on the other thing, and contingency table probably is just a way of displaying data as opposed to chi-square. It's the chi-squared test that gives us a way to use this data. So the chi-squared test would give us a way of using this data, And we are starting with null hypothesis significance testing, NHST. We are going to be getting some test assumptions, parameters of interest, and then a null hypothesis, test statistics, and null distribution. Okay, I think I can pause now and see where this video leads. Okay, we are back and we have seen the entire video. So this is the initial reaction. The initial reaction is that this is quite complex and I am very confused about plenty of stuff in the middle portion, but what I do know for sure is that the chi-square test is a hypothesis test for categorical data. So we had binomial and Bernoulli distributions and their use. Their use probably is not applicable to hypothesis testing. Like, how would you take those things and create a hypothesis test on that? Probably this is why categorical tests that require a hypothesis testing, especially given the scenario of a clinical trial of a drug that did something and that probably did not do something, and then again comparing that said drug to a placebo would require a chi-square test of this sort. So this is like the why we would even bother with the chi-square distribution. But that being said, we have plenty to cover, and
my work is easy because I use ClickUp here.
And I think the best way to go about that would be to probably read through the entirety
For the statistic
text. So the first thing that I want to, the categories are mutually exclusive. Yes, we have that. And then we have a random sample IID, and the sample size has to be large enough. We understand that part as well. And this probably also talking about the probability of one giving out the probability of the other one. For instance, if you know how many people the treatment, how many diseases, sinuses, like what was this, like drug treating, whatever, the treatment resolved this portion of people's problem. So what would be the opposite of that? 1 minus this is basically giving the amount of people that the drug did not help. So have their own probability of resolving migraine. So you can also think of this probability being a condition, being conditioned on the treatment group. What we want to see is that people in the treatment group have a higher probability of their migraines stopping compared to the placebo group. Okay, higher probability of the people. So for instance, there is an idea that we want this probability to be higher than this probability, right? So we have the own probability of resolving the migraine. So you can also think of this probability as being conditioned to the treatment group. What we want to see is, okay, I've read through this. So then you have condition which group they were in. Yeah, so the treatment group, as I mentioned, should be the probability of the treatment group, probability given the treatment should be higher than the probability given the placebo. This would be the alternative hypothesis, I guess, or the null hypothesis, right? So the null hypothesis, that was the alternative hypothesis. The null one is that they both generate the same probability. We have heard it before. Okay, and before you may have heard it referred to as chi-square test of independence from the perspective of independence. The null hypothesis is what the null hypothesis is that the outcome is independent of treatment group. The distribution doesn't change no matter what treatment group it's conditioned on. Then these two variables are considered to be independent of each other. This is the little definition of independence from a probability perspective. A contingency table just displays data we need to construct the statistic based off. We need to test statistics to summarize the data in the table. Okay, then we go, I guess, and resolve. The treatment looks like it works. Okay, yeah, so this probably looks like it works because it resolved more than it did not unresolved. Wait, what did I say? The clear winner is that the drug affected like 63 people and did not affect like 37 people. And the idea is like the idea is that did it do as good a job as a placebo? That would be like the hypothesis. The hypothesis is that it did not. Both are kind of same. And the alternative hypothesis that is that it did, and probably the treatment probability is higher than the placebo one. So we created dummy hypothesis. So this would be the dummy hypothesis that these two probabilities are equal. You can calculate the null contains uniform margins of data. Okay. Observed and expected counts constituted, and use the first. Difference between what we observe and okay. And does this seem familiar? The actual observed data minus the difference between expected data, I guess, expected counts. Yes. This should seem familiar because this is the x minus expected value of x squared that we did in many of the things, such as chapter 6 of probability. So this is that formula. So this is like the squared element comes in. So yes, variance, we tested for variance in just normal regression models and stuff like that. So this should seem very familiar. And we divided by the expected value. So dividing by expected value, this one I don't remember. Like, did we do this or did we divide by the number of values or variables that we had received? So this probably would be the distinction between the two. It reflects the fact that the chi-square test needs a large sample size to be reliable. Okay. And then we are counting I equal 1 to j equal 1 to 2. Do this calculation for all of the cells and then add everything up in sum. I think this is where I lose track of the video. So this is like 8 minutes in and I have no idea what, like, why are we doing this I and j. And the has a chi-squared, the test statistics has a chi-squared distribution. So I have to understand better test statistic, like the t distribution in general, how that works. And we are like this should seem familiar. Like test statistics is just this, like expected divided by the mean is like the expected value. Standardized simple mean, this is the standardized simple mean. Okay, and last thing that I would talk about is the degree of freedom. So chi-square distribution probably was the reason it came to my attention to begin with, was the idea about degrees of freedom and how different degrees of freedom has different statistical parametric family. So this is probably where heavy research should come into play. And as I post this particular reading of this, like not reading but at this particular like go through of this video, I am going to do a thorough research on this as well. It can be standardized if like there is no degree of freedom. Like in this particular one there's no degree of freedom, but they both have this familiar standardized form. Okay, it's almost similar. Expected observed minus expected and root of this, and this one was a function of just the number. The x squared test, the chi-square test of goodness to fit. And this paper contains an expository discussion of the chi-square test of goodness of fit, intended for the student and the user of statistical theory rather than for the expert. Part 1 describes the historical development of the distribution theory on which the test rests. Probably I should understand that what that is. Research bearing on the particular application of the test, in particular on the minimum expected number per class and the construction of classes, is discussed in part 2. Some varied options about the extent to which the test actually is useful to the scientists are presented in part 3. Part 4 outlines a number of tests that have been proposed as substitutes for the chi-square test, the omega square test and the smooth test and the likelihood ratio test. And part 5 is a number of supplementary tests, the run test based on low moments, subdivision and chi-square into components. Okay. Some square standard normalized normals. Okay. Okay, so this probably would be the last thing that happens. The normal distribution just like this, and chi-square distribution is this, and different degrees of freedom gives different outcomes, results. Normal produces chi-square distribution. Summing independent normals produces a chi-square distribution. Again, this kind of statements needs to be thoroughly understood through use of AI. Summing independent normals produces a chi-square distribution. What? I have no idea what this is. Okay, so more or less I do not understand. Probably from the 8-minute like this mark onward, I do not understand, and I need to understand. Probably I would do so through watching another video. So what would be the other video I should watch? Which one? Let's give JB statistics a try and pause the video for now. Okay, we are back after a while, and last time we were here we had a confusion about this particular formula, because I did not understand why were we dividing it by the expected value, which is like 10. So this example kind of clarifies that. For instance, the E here is a placeholder for frequency, or not frequency but N, right? N or F, yeah, frequency, why not? So the frequency, the expected frequency with which you think that the particular observation would come out. For instance, if we are like rolling a dice 60 times, 1 2 3 4 5 and 6 would have equal probability of, like, equal frequency of 10 is the expectation. That's why we are dividing it by 10 all the time, and we are using a squared distance from square distance from the value that we got from the expected value, and like the squaring it would give us the additional benefit of not dealing with negatives. So the graph would be something like this, just on the positive side, and we would look into better looking graphs. But this is probably the gist of it. And the second critical thing, which is beyond just the structure or the understanding, is the actual use. The actual use here is that chi-square is 1.6, like the outcome of this formula is 1.6. Now if the null hypothesis, that is the die-sphere, is true, then this value 1.6 is the value from the chi-square distribution with degrees of freedom 6 minus 1, because we had a 6. Okay, we only had like 6 observations, right? 1 2 3 4 5 6 observations, or 6-sided die. 6 observation, I think, is the idea. We would now compare 1.6. So 1.6 would be the critical value. For normal distributions, we had we could have used a Z statistics, for instance, like the normal Z statistics chi-square. Okay, never mind. For a normal For a data that was parametric and normally distributed, we would use 1.6 the z test as a means of finding the critical value. Yes, so the outcome is just the critical value. So we can use the critical value approach, or we can use the p-value approach to see if the hypothesis that we concocted works or doesn't work. So where would we start? I think after saying that, there was this additional confusion about like what did it mean from the previous video to like add the squares. I think this explanation does a better, not a better, but a good decent enough job. Why is chi-square defined as a sum squared normal of normal? Let me read that again. Part 1. Why is chi-squared defined as a sum of squared normal variables? Let's suppose we take one random variable z, like by the way, this notation, like zero mean is in the zero, like imagine a bell curve, and variation of 1, not variation but standard deviation of 1. So this is a standardized form, right? Random variable z, and probably z denotes standardized form. So say you take 3 such independent random variables, this and that. Now compute z squared. The sum of the squares defines a chi-squared random variable with 3 degrees of freedom denoted. It is not based on data yet. We have not yet used this in this particular data, or we have not yet used any particular data to see through this. Like, this is just theoretical. If you square and sum up n independent standard normals, their distribution is called a chi-square with n degrees of freedom. So the chi-square distribution exists before you even look at a categorical frequencies. Okay, again, the word frequencies is kind of important too. Why does this statistic follow a chi-squared? Why does this statistic follow a chi-square distribution? Let's zoom in on that. So a difference between observed and expected, a residual, is squared always positive, squared by the variance. It is scaled by the variance, and we will look into the scaled aspect of it. As sample size grows, the central limit theorem tells us that it approximates a normal standardized thing. So the only confusion from this is like, why did a root get into this? Like, did we, I understand actually. So we had this, we square rooted everything, so the square and the root cut out, and we were left with just this. But the question then is, like, when we were dealing this when we were doing this with normal distributions and z-scores, the idea was that the observations were not categorical, and here we have a categorical thing, right? So what I really meant to say was, when we were dealing with normal distributions and like z-scores, we are also dealing with population parameter, like not population parameter, like variance or the population mean. So that was something, and that is why we had like square root, and we had to do some work on the data to make the inference that we are making more palatable to the overall population. So compared to that, are we doing the same thing here when like we took a square root of this term to get this term? Like, was that the idea behind this as well, that because we cannot know true population mean or true population variance, we have to square root the entire thing to make it more palatable? Is it the rationale? I will not Google it, but I will I will use Gemini or ChatGPT to figure that one out. Let me do it right now actually. Okay, I am back and I have seen this video. This video from JB Statistics, an introduction to chi-square distribution, is amazing. So it starts off with this, goes to like defining. The first thing that I have to take note of is that the chi-square distribution is a continuous probability distribution that is widely used in, it's a continuous one. I did not know. I thought because this probably is unparametric, it would not be continuous, but apparently it is continuous, and it did such a great job in delineating that delineating few things actually. So the first thing is that the standard normal distribution with mean 0 and standard deviation of 1 degree freedom of, like 1 degree freedom chi-square is just this. This is like, it has 1 degree of freedom, and with 1 degree of freedom, yes. This one we covered here. And this is the distribution, and the nice thing about this video is it brings back gamma function. Gamma function was the original reason I wanted to learn this. I remember watching the machine learning video. I think this one would be the machine learning one. Okay, this one, this particular video on machine learning. I wanted to study, basically I wanted to know more about statistics and the different aspects and tests of statistics. So the starting point was gamma function, and gamma function related to chi-square distribution in some way. So this is the reason. Maybe I started my path again. I'm like deviating from the topic, but this was cool. This looks so much like normal distribution. Let me check out the normal distribution one. Normal distribution one is 1 divided by sigma, and normal distribution has 1 divided by sigma root over 2 pi. So normal deviation has pi, and it's multiplied with Euler's -1/2 times x minus mu, which is the expected value, minus sigma square. So don't see anything like that here, but this one deals with degrees of freedom k. This portion is somewhat similar. Euler's constant it is here as well, but in any case, this particular thing has uses. For instance, like we can add something. I think this particular video mentions that by differentiating or integrating this function, we can like get some number, which should be useful. If I had like time, I could probably check out like the use of it, direct use of it. But the relationship is okay. This also talks about mean. For instance, the mean for this chi-square distribution is just the degree of freedom k, and the standard deviation is 2k, and it is also mentioned here. Like everything that I said basically is mentioned here. 1 degree, 2 degree, 3 degree, and at a certain point it converges, but the mean is just the degree of freedom, and standard deviation, not standard deviation, yeah, standard deviation is like 2 times the mean. So you can see that here. Okay, 2, basically twice that. At 90 it probably converges. Yes, mean k, mode is k minus 2, mode is basically the highest point. So if this one has 92 degrees of freedom, no, okay, so degrees of freedom is 90, so the mode would be at this point, the highest peak would be 88. Variance is 2k, standard deviation is root. Okay, I'm sorry, I was saying it I was saying it wrong. Variance is 2k, standard deviation is root 2k. Range is 0 to infinity. Symmetry asymmetrical, right skewed. So you will see this is like, it becomes extremely right skewed. For instance, here you can see like right skewed. minimum 0, maximum 0. Okay, this is like the right skewed element. Talks about mode, etc. Areas and percentile for the, okay, yes, areas. To find the areas you have to integrate it, and you will find the areas under it, area under it. Now that I've said that, I remember where I left off the last time I paused. I left off here. I was wondering, recap of what you're referring to. You wrote, why did we square root this part? This part is the familiar part that we know, and why did we square root this part? To transform to basically transform this transformation turns a variable into something that has mean of 0, variance of 1. That's why we transform. So variance, just the root of that, basically becomes this one. Standard deviation basically means that 2 times the variance, and once we transform it, it becomes this. Squaring the standardized difference. Once you've got a standardized once you've got a standard normal variable zi, then zi square is just going to be this is why you see the square root in the denominator. Is there to standardize the residual, standardizing the residual, right? Standardizing y, wait, transform and standardize. Okay, standardize. Let's read the summary. The square root in the denominator comes from the standard deviation square root of square root of variance. We standardize O to get observed value minus expected value to get something that behave like standard normal. We then square it to get chi-squared value. This is building block for full chi-square test. Putting it together, the raw difference between observed and expected, the standardized difference, z-score. So this is basically the z-score version of it, and the idea to understand it is to understand, like, we do this very thing for normal distribution. And I was wrong, by the way. I should have started this video by saying, like, not this video, but should have started this recording portion post the pause pause the resume, by stating that I was wrong in my previous explanation or previous expectation about why it was here. I think I said something along the lines of it was there to account for the population parameter that we didn't know, but no, this is here to just standardize the thing, just the standardizing mechanism. And similar thing probably happens in normal distribution as well. A chi-square component with 1 degree of freedom. Okay, I guess this has been a good thing. This has been a good thing as well. Let me pause and see what else can I start with or go from here. Yes, we are back once again, and like these two videos are super awesome. So the first one is this one, an introduction to T distribution. This one is much more fast forward and gets directly into this, like, okay. Let me set this up properly. So I have been wondering for a while, starting from maybe 2 or 3 days ago, especially since beginning to record this session, is why do I not know what chi-square distribution is? Like, for instance, I heard the term chi-square distribution, but I didn't quite know what it was. But I knew T distribution, I knew the normal distribution. So what went wrong? So this is why I think, not this is why, but this is what I think went wrong. So for instance, normal distribution and T distributions are related, and probably chi-square distribution sits in the middle of it. So you start with normal and then you learn something about chi-square distribution, and then using chi-square distribution you formulate T test or like T distribution, right? So Z is a standard normal distribution. U has chi-square distribution with this V sample is called a mu degrees of freedom. Z and U are independent. So if we divide the standard normal distribution value divided by like U root over mu divided by mu, and we like square root it, we get something called a T distribution. So this is the basic gist of it. If we are drawing n independent observations from a normal distributed population with a mean mu and a variance sigma squared, then this is like the normal distribution has a T distribution. Oh wait, sorry. Okay, if you're drawing any independent observations for a non-distributed population with mu and variance. Okay, so this is I think where we should go to the next video, because the next video outlines why, like how did it happen. So for instance, this is the formula that we know for normal distribution. Z-score for normal distribution is something that we get from this formula, but here's a catch: this population standard deviation we do not know. So what we do is we use the sample standard deviation, and as we use the sample standard deviation, we get 1 degree of freedom. We have heard that. The question is, why do we get 1 degree of freedom? It has something to do with variance. Like, I think the explanation given to us in like in MN's class plus in different statistical or finance class that we did, my understanding was it had something to do with variance. Like, variance has a square, and we need square for variance because we don't want to have half of the data cross out the other half. That's why we have to, like, how do I phrase it? That's why we have to, like, blow it out of proportion. And once we do that, and hence we use the square, and once we do that, we have kind of a better gauge. But the byproduct of which is, like, because we are squaring it, we have 1 degree of freedom. That probably was the idea. But now that we are understanding or learning about degrees of freedom, which is basically like how we, so for instance, the example, I don't know where I got this example from, but rolling a dice. Is rolling a dice a better example or something else? Yeah, like adding 3 numbers, okay? 10, 5 and 5. So if the first number is 10, the second number is 5, and you know the sum of the 3 numbers added is basically like 20, so you have 1 degree of freedom, right? So that is the idea. And this video and this video too will show how t distribution, when we add another degree of freedom, converges to normal distribution. So that is what we have. Is like t distribution with 1 standard degree of freedom and heavier tail, but the tail is never quite like converging with this, and as a result confidence interval, like 95% confidence, like this portion, this has a critical value of 1.9, and once we totally have converged with normal distribution, if we like drew a line here, the t distribution would also have a value of 1.9. I think it takes like 90 some degrees of freedom to achieve that, but we go in, and this is like the calculation, like okay, so infinite, not even 90 but infinite. Like even if we have like 100 variables, like 100 observations, 1.98, not 96. But we are told on a regular basis that n should be like less than, like higher than 90, right? Higher than 90, I think like it would fall into here, 2.042 here. Higher than 30, sorry, did I say 90? Higher than 30. So this is basically the idea, and like he basically tells you that we shouldn't fall into that trap. Some sources say that if n is higher than 30, forget about t and use the standard normal distribution, but he's saying that no, we should not forget about t, and we should be using if we use z, we should be using if we use z when we should be using t, our calculated margins of error will be smaller than it should be. So we would have more error, and we need to account for that. Any case, that was the video, and this one basically highlights that, like we can go from this video to that video and like finish this video and then come back here, and it would make sense. Has t distribution with n-1 degrees of freedom, sample mean, sample standard deviation. The t distribution often arises in statistical inference on means when we are sampling from a normal distributed population. So probably I think here the JB statistic gave some commentary that we do not use t distributions much, and even like dealing with the actual formula, the like distribution equation. Yeah, probably distribution equation is probably like less used, something along that line. So with the distribution with mu degrees of freedom is basically this is like a gamma function again. Gamma function should be like a higher than 0, median is 0, mu is 0 for mu of higher than 1, and variance is this like sigma square, so this is variance. As the degrees of freedom increases, the distribution tends towards this. So these are like characteristics I probably should have in mind, and the idea would be to check this against books like this, right? So if we are dealing with chi-square distribution here, and by the way, I started with just the sampling distribution for statistics, again makes so much sense because we are not dealing with a population, we're dealing with statistics, and statistics comes with what? Statistics tend to be normal, but the idea that the complication here is about how many statistics would, when combined, would tend toward normal, probably is the idea. Estimator, okay, we go through this, we are introduced to chi-square distribution. Let's see now, let's roll through this to see if things seem familiar. The family of chi-square distributions is a subcollection of family of a gamma distribution. We will probably have to like set gamma distributions aside for now. Let's focus on just learning about chi-square distribution. The special gamma distributions arise as sampling distribution of variance estimators based on random samples from a normal distribution. Arise as sampling distributions of variance estimators. Sampling distribution of variance. Again, remember in this video when he said that it depended on variance, like here, depended on variance. Which one here? I think here it was said that determines the sample variance of n-1, so it depends on variance to some extent. Based on random samples from a normal distribution. I think the idea, the complication again is like how many random samples, okay. Definition and distribution, they're going with this, this is like a gamma function m-2, okay. Properties of distribution, theorem 1, mean and variance. Wow. Moment generating function, I have no idea what this is. If random variable x has x distribution, m degrees of freedom, expected mean is this, and expected variance is this. Furthermore, it follows that moment generating function given eq x is that, like, I have to totally understand like what this is. I don't understand moment generating function. Like, can I like should I do it? Let's go. Where should I go? I can explain this one. You're asking about a very important, okay. Let it do its job. The random variable x, let f of which notice from the PDF and also CDF cumulative distribution function probability of something. I don't want to even like understand what this is. Summary, just read the summary. The chi-square distribution with n degrees of freedom is the same as a gamma distribution with parameters m divided by 2 and half, like gamma distribution of this. So I guess I have to understand even gamma distribution if I want to fully understand chapter 8. But then again, it referred to chapter 5, so maybe I'm jumping the shark here. Jumping the shark here. I probably should be better off understanding or reading through chapter 5 and then come back here, and a better approach of that would be like starting with chapter 1. Now that I have figured out how to like go about creating an incentive structure around how I study. For instance, like I'll record, I will read, check out videos, and then I'll just summarize that and like go through that and like hit resume as I do it. So let's leave gamma function for that. It is distribution of the sum of squares of samples of n independent standard normal random variables. The mean of the chi-square distribution with m degrees of freedom is m and the variance is 2m. Okay, we have that. Joint distribution of sample means and sample variables. So like double t square, like double t distribution, etc. So let's read through this. Suppose that our data from a random sample from a normal suppose that our data from a random sample from a normal distribution. The sample mean mu and random sample variance are important statistics that are computed in order to estimate the parameters of the normal distribution. Their marginal distributions help us understand how good each of them is as an estimator of the corresponding parameter. However, the marginal distribution of mu hat depends on sigma. The joint distribution will also depend difference. Okay, this has to go directly to ChatGPT as well to help me explain understand what the problem suggests. But let me read through, let me just scroll through this. Estimation of mean and standard deviation. This looks normal to me so far. Proof of theorem, orthogonal matrix. Okay, it's dealing with matrix and proving some property of that standard normal deviation. Okay, this is a high-end course, I guess. Let x1 to xn be a random sample from a normal distribution with mean mu and variance sigma squared. Then the sample mean and sample variance are independent random variables. Furthermore, mu has the normal distribution with mean mu and variance this, and n, what is this? Okay, n variance square divided by the variance square has a chi-square distribution with n minus 1 degrees of freedom. I think I understand what this means. This is basically saying the OI, or the observed value, minus EI squared would just be the EI squared. Like this is like serving as a placeholder for estimate excuse me, serving as a placeholder for estimated value or estimated variable, probably. Most likely not, because it has like square terms, like the variance didn't have square, right? The variance was not square, so when we like rooted it, it became a root. So again, this like we'll have to get into it, exercises, and I probably have to deal with the exercises as well. Okay, 8.4 is the t distribution. When our data are a sample from a normal distribution, mean, mu and variance, and the distribution half is a standard normal distribution where means mean unknown and we can replace distributor. We can replace sigma by an estimator in the unknown. Okay, so this is like talking about gamma functions and stuff, so this should include plenty of relation to the Chauncey distribution, to the standard normal distribution. Okay, derivative PDF, like it is deriving PDF. This is the same thing as we learned in like introductory course, but this comes with much more proof and like much more rigorous understanding, defining of like how the things we came to know came about. Confidence intervals for mean and normal distribution. Okay, this contribute. Okay, when will this chapter finish? The confidence independence. I don't know what to read. Bayesian analysis and of samples from a normal distribution. Bayesian. Okay, we have Bayesian ones, then unbiased estimators, so it's like start, we have to do it. Unbiased estimators, Fisher information. Okay, supplementary exercise. This is like an entire chapter. All of this going on record. Is this a good thing that I'm doing? I probably should have like studied it in my free time, I guess. Yeah, let's just go out of this thing right now. So we were here. Okay, I'm just going to read this and then probably going to be done for the day, I think. You're asking about a very important property of chi-square distribution and how it is derived from a moment generating function MGF. Let's carefully break this down. The moment generating function MGF. The moment generating function of a random variable x is defined as it generates moments, means, variance, etc., and also uniquely characterizes the distribution. If two random variables have they have the same distribution. Okay. Distribution m degrees of freedom for x. What is this? Yeah, I officially do not understand any of this concept. MGF. Okay, I think I'm going to pause and then come back with a summary and a rundown and be done for the day. Okay, we are at the finishing line and we are just going to summarize what we have done so far. So we started with chi-square distribution, and this is like what the thread looked like on ChatGPT. I asked what was a parametric test. In response to this, like chi-square test is a non-parametric test used to analyze categorical data. I was a bit confused about what was categorical data and definitely didn't know what was a parametric or non-parametric test, so that's why I was here. So what is a non-parametric test? It does not assume a specific distribution. So chi-square tests do not assume a specific distribution. It's basically kind of like, remember when we said it has a mean of degrees of freedom and the variance is just like 2 times that. So that's why probably it does not assume any distribution, but coupled with normal distribution, when we define normal distribution by chi-square distribution, we get t distributions. So that is basically the idea. But here's some non-parametric tests. Chi-square frequency counts, Mann-Whitney U test, non-parametric alternative to t test. Okay, one-way ANOVA for paired samples without assessing normalcy. Okay, and then I asked about some of these that I but I got from here, like chi-square distribution population mean. This is from, like, let me get the URL. Chi-square distribution population mean. Okay, so this one, and I also should get the from here. So we are basically getting the description, like not description, but we asked like what did it mean, and ChatGPT complied, answered very nicely, stuff like that. So I'm just going to copy the response. GPT link. Holy shit! No, just one the. This is brutal and bad. I want this one actually. Copy link. Yes, thank you. Link copied. So GPT. Oh no! No! What the fuck? Hey, I thought I like copied the link. So I copied the link. What happened? Okay, I copied the link. So how else would I like get the specific chat copy? how else would I get a specific channel? uh, what should I do here? I should like pause the main video and figure this out. Okay, I think I have figured this one out. It should be this. And then we have double bits like scriber double b. Scriber link is no. Scriber came with a good amount of insights as well. So everything we learned, or at least I learned in JB statistics video, I think could be found in Scriber as well. So I'm just going to close the tab. ChatGPT, okay, close the tab for now. Let's close the tab for now. Then we have Gemini, and Gemini started with like parametric, non-parametric, how chi-square tests differ from normal distribution, t distribution, data type like categorical, one is continuous, other one is okay. So apparently chi-square test is also, oh right, chi-square test is not categorical, like not continuous, but t tests are, okay, t tests are continuous numerical. So it like gives you a good perspective on the difference between chi-square tests and normal. Like it's categorical, it's continuous, it's like continuous question underlying distribution. Chi-square distribution doesn't probably, I thought, take any particular distribution, but again, who cares. Z distribution, students t distribution. Okay, in summary, this observation, yeah, you're largely correct here. Is a t-test just a normal distribution with less observations? Largely, not entirely. Largely because, okay, fine, I got somewhat of the intuitive idea, like the once you lay out the true reason, this could be an intuitive way of understanding it, grasping it. So the real reason is that we don't know the population parameter, sigma. So that's why we are using the sample standard deviations to make do. So this is just that. Degree of freedoms of the relator, so it discusses the degree of freedom, and also in chi-square test, goodness of fit test. For goodness of fit test C categories, the degrees of freedom are typically this degrees of categories. Two test of independence for chi-square distribution, chi-square tests of independence in a contingency table, R rows and C columns, and we were doing contingency tables for very normal video. This is the idea: R minus 1, C minus 1. Copied in sponsor share conversation. Generate me a link. Okay, link copied. Copy link. I hope this one would work. Okay. Now just for the last thing, we have this video. Chi-square copy should go here. Then we have this video. And lastly, we have a normal video from JB statistics. This one. Oh, wow. Logistic regression explaining ANOVA and F tests. Okay, one of these days. So where chi-square distribution video? Oh no, this one is not it. Oh no, this is also messed up, and I'll probably have to get rid of the one to this one. Just one more video to go, which is like this one, and we're done. Okay, we are done with this portion, and now lastly all I'm going to do is go and check out the main book that I'm reading from, and I'm just going to make some basic predictions and like talks, generalized talks, and it will be very small because I'll just summarize stuff. Okay, we are just going to conclude this video, and let me start off by saying that the recording format, like pausing and then like watching a video, commenting on that video, and like speeding through it really helped me a lot. Not only but not limited to, but to a great extent, because I can have more clarity of thought, and it like reduces the awkwardness of silence, or me just like going about and not understanding what to do. So that level of new amateurish awkwardness is like totally eliminated if I can pause and like understand something and then like resume. Also helps me focus in terms of like watching the video itself. I can like have with great focus and great clarity and great incentive to like watch something and not waste time and not be distracted by something else. Watch that video and like resume. So like pausing, watching something with a focused alertness, and then like going back to the original recording session like totally helped, absolutely helped. And towards the latter portion of this particular video, I kind of lost track of that. So I probably should have not done that. I should have tried to condense the video to the extent that I could. So that means that the whole ordeal about getting this done should have been done under the not under the, but should have done entirely on my own time, right? And also I spent some time just like scrolling through chapter 8, which was it a mistake or was it something like useful? It was probably a mistake, precisely because the viewers are not going to enjoy that portion. Just like I mean, in this portion I am at least adding commentary. In that portion I was just like scrolling through stuff. But anyhow, let's do one last dive of the book. The book itself, I like Probability and Statistic, 4th edition, De Groot. De Groot's book is meant for whom, by the way? I don't know who this is meant for, but this is really high end. I have read, I think, set theory portion, definition, probability, finite sample spaces, etc., etc., multinomial coefficients. I don't know what that is. So I have done a like sparring session with chapter 1. Probably you can handle chapter 2. Random variables, like sure. Different distributions like random variables and discrete distribution, continuous, marginal, conditional, multivariate distribution, function of random variables. This portion would be really useful in understanding the different distributions, because I have a low understanding of distributions. I don't understand, for instance, gamma distribution. I probably do not have a sufficient view or understanding of all the different distributions. I know few, for instance, like Poisson or like normal, uniform, Bernoulli, binomial. These are like the common types. So that would be welcome to understand, especially the Bernoulli one, because I have been like just like this video, I want to learn about binomial distribution as well. So visualize JB statistics and like all the other content creators I can like learn from. Expectation, chapter 4, expectation, random variables, covariance and correlation, mean, conditional exclusivity. Okay, this one should not be that much of an issue. Chapter 5 is really important, if not for anything, for gamma distribution, right? Then we have beta distribution, multinomial distribution, birate, normal distribution. All the distributions I should be learning. Large random samples, central limit theorem, estimation, statistical inference, prior and posterior distribution, conjugate prior distributions. This should be interesting as well. Chapter 8 I am currently reading. I read today some portion. It like introduced a great deal of stuff that I did not know, and in the subsequent lectures like there could be two approaches, which is like I start from chapter 1 and then go to 2, 3, 4 and subsequent ones. There is a much more fast-paced approach to that, which is something I think it might be worth pursuing, because I like if I follow that chain of sequence it gets boring. So a better approach might as well be like going straight to what is a gamma function, going straight to what is a moment generative function, going straight to what are like F distribution, stuff like that. But for that I feel like I need chapter 3 in particular and chapter 5. So chapter 3 and chapter 5 should like set me free in that regard. And then the last one would be hypothesis testing. I know somewhat hypothesis testing, so I should just revamp on that. Try to do some codes as I go along. Categorical and non-parametric methods. Okay, wow, yeah, this is nice that like categorical data and non-parametric methods are integrated here. So I probably would find some sample problems that I would need to do. Linear statistical models, the method of least squares, regression, statistical inference in simple linear regression, Bayesian influence in simple linear regression, general linear model and multiple regression, analysis of variance, two-way layout, two-way replication. Okay, this like seems like totally related with the machine learning thing that I wanted to do. Solutions, simulation. What is simulation? Simulation useful or not? Markov chain, Monte Carlo, the bootstrap supplement exercises. So the last thing that I want to say is like, how many years is this thing going to take me? I think I am not going to be finished until mid like 2027. So that would mean how many days? 365 plus 365, 720 days, 720 more days. I don't think I would be finished entirely, like to the extent that I want up until that point. That's my idea, that's my imagination. Not because of what, only because it's going to take like, this is going to be the maximum amount of time I can do this. I think there is a minimum amount of time I can do this as well. So let me put that here, mid 2026. Like if I can accelerate somehow, how many more sessions would it take is the question actually. How many more sessions? How many more sessions? How many sessions? Today was one. I can do that. I can do another one in like how many days? Like how many days would it take for me to understand the basics properly? For instance, the F distributions and stuff like that, the hypothesis tests. I think like 4 to 7. 4 would be like 6 to 8 sessions. So that is like just going to be 6 to 8 weeks. How many months? 8 weeks is going to like end 3 months. Let's see, 3 months. 3 months, right? I have 3 months. Why? 3 months, and I can do how many more additional sessions would it take to do the basic course? Okay, the basic stuff would be like 2 months. I will be absolutely like untouchable there. And then there is going to be the difficult part like the moment gathering function, stuff like that, and like the secondary statistics in general. So for instance, if I compare by CFA standard, the secondary ones would be like CFA level 2, CFA level 3, they do different risk assessment, etc., etc. So I think to do that I at least 3 doubles, so 18 to how many else, 18 to 24 weeks, right? So that means it's going to take me 6 months, or yeah, almost 6 months, 6 to 7 months. Level 2 stuff. So levels 2, once I am done with level 2, I think I should be able to handle this book. This book is big, but these are not that difficult. So I think if this this follows, I should be able to do this within like mid 2016. 3 months for this, and like 7 months for what? For the basic stuff. Sorry, for the difficult stuff, like learning new stuff with respect to statistics, with respect to CFA level 2. I think the CFA level 2 curriculum is not going to be a difficult one, like not going to be a bad choice. Like I know what I have to do for a level 1, which is basically what I did for university first year, and this book looks like something that we do in a second to third year, because it introduces lots of functions and like different properties of functions. So June 2026, I think I should be able to finish this book. Would be absolutely a piece of cake, and I should be able to do this. So with that being said, I'm going to pause for now, and I think I'm going to stop recording.